Okay, so let's continue from where we left off last time. As a quick recap here, we started talking about memory management. So this is really the problem of how the OS allocates memory to processes. Okay, we looked at the simplest possible approach, which is contiguous allocation. Okay, in contiguous allocation, the OS is going to allocate a contiguous chunk of RAM to each process. Okay, we looked at two schemes, static relocation and dynamic relocation. Right? Both of these schemes are necessary because in multi-programming environment, more than one process may be resident in memory. Right? But when you compile the process from source code, or rather compile the program from source code, the compiler doesn't know where the process is going to reside in memory. Okay, so any assembly instructions that has a memory operand, okay, cannot be determined at compile time because you do not know where the process resides in memory. Okay, you do not know where a variable will be stored. All you can figure out is what is the address with respect to the start of the process, assuming it's contiguously laid out. Okay, so the only thing compiler can do is generate virtual addresses that are relative to the start of the address. But when a process is then loaded in memory, you have to translate that virtual address into a physical address, into a real address, because the assembly instruction in the end has to, if it has a memory operand, has to have a real address of within the RAM. Okay? In static relocation, this translation is done at load time. When a process is actually loaded into RAM, okay, the loader is going to figure out where the process starts. It's going to look at each assembly instruction, okay, and it's going to plug in the right memory address, because it's going to look at what the virtual address, do the translation to physical and plug it in. Okay. In dynamic relocation, this translation is done at runtime. Okay. There is hardware that is going to take a virtual address. Okay, there is a base register which stores the starting address of each process. Okay. So a real address is simply taking the offset with respect to the start of the process and adding that to the start address. That gives you a real address. Okay. There is hardware logic that allows us to do that, okay, which is this picture that I showed you last time. There is a base register, also referred to as a relocation register. So assembly instructions generate logical addresses. That's an offset with respect to the start of the process. You take the offset, you take the start address, you sum the two, you get a real address. Okay, so that's what dynamic relocation does. So I'll have a little bit more to say about contiguous allocation today, but much of our time is going to be spent on a new memory management scheme called paging. Okay, and we'll talk about what paging is and why we need in just a moment. Let me first finish the material from last time that we didn't cover. Okay, so as I had mentioned, the big problem with contiguous allocation is that it leads to fragmentation of memory. Over time, as processes come and go, your memory space gets divided up into regions that are allocated to processes and holes that are unallocated. Okay? And so you have all these holes spread across RAM. That leads to fragmentation. External fragmentation occurs when in the aggregate you may have enough free memory, but there isn't any one hole that's big enough to hold a process. Okay, so you may say I have, let's say, 1 megabyte of RAM, okay, but it's all spread across in tiny chunks. So if a process comes in and says I need 1 megabyte, you cannot give it 1 megabyte because you don't have a contiguous chunk. Okay? And we talked about this notion of compaction, okay, which is essentially defragmentation. Okay, so the picture for external fragmentation is shown above. Okay, so here you have the OS processes D, C, and D loaded in RAM, and you have three holes that are shown in gray. Okay? Process E comes along and says it needs 600 bytes. Okay? Now, in the aggregate, if you add up the sizes of those holes, you have more than 600 bytes free, but there isn't any one hole that is going to give you that 600 bytes. So you have to either say that you do not have a hole large enough and deny the request, which essentially means you cannot even start that process. You say out of memory and you just give an error, or you have to run defragmentation, which is basically going to translate the memory picture from this to this, where C and D are moved up. Okay, they're basically copied over, so you essentially defragmented memory and constructed one large hole from these little holes. Okay? Once you do that, then you have enough space to accommodate E, which is what happens there. Okay? Defragmentation is expensive. It involves memory copying, which is a slow process. So you do not want to run this frequently. Okay, so if you have contiguous allocation, this is done every once in a while. Okay. What is shown here is full defragmentation, where all the processes are sort of compacted and you create one big hole. Okay. Now you can also do partial defragmentation, which is shown here, which is you move enough processes to create a hole large enough for E. Okay. So E comes along and says, I need 600 bytes. You say there's no hole that's big enough. Let's see what are some small number of processes that can be moved around to construct that hole. In this case, the simplest thing to do is to move D up, so that this hole and this hole, these two holes get combined, and that is a 800 byte hole that's still large enough to accommodate E. Okay, so you're not going to run full defragment. Okay, you're going to do partial and just extract enough free space to accommodate this process. Okay. This is somewhat cheaper to do, clearly, because you don't need to move everything, okay, in order to defragment. So there are different policies that you can decide on to do compaction or defragmentation, but nevertheless you have to move memory around. Okay. Okay. So now let's assume that you have contiguous allocation. Another limitation. First limitation was you have fragmentation, and you have to occasionally run compaction algorithms or defragmentation algorithms to extract free space back into one larger hole. The other problem is we are assuming that the entire process is always resident in memory at all times. Okay. So what this says is, let's, after defragmentation, if some new processes come along and both those holes here get filled up, okay, you are run out of memory. If a new process comes along at that point, okay, if you do not do anything else, you are going to say, I do not have memory to run this process, and you are going to deny that request. You cannot start that process up. Okay? That's one option. The other option is you could do something a little smarter and say that why not multiplex between processes? Why have them be resident in my RAM at all times? That is not required. You only need the process to be actually in memory when it is scheduled for execution. If it's waiting for I/O, there is no need for a process to just sit there and occupy RAM space. Okay, so you can use a technique called swapping. Okay. So what happens in swapping is you can take a running process that's resident in memory, and you can just take all of its memory state and put it on disk temporarily, okay, while it is not running. And when it's about to execute again, you bring it back. Okay, so you can swap processes in and out. The entire processes get swapped in and out. What this allows you to do is, if memory fills up, okay, by processes, you can take some processes which may be waiting on I/O, waiting on locks, but they're not running, and hence they're not making any use of RAM at that point. You can swap them out and bring in other processes that are about to execute. Okay? So by carefully managing your RAM space, you can have more processes running than you have RAM for. Okay? This is one way by which you can relax the restriction that all processes have to be resident in RAM at all times in contiguous allocation. If you do that, then you will be limited by the space you have for main memory. If you try to start more processes than you have RAM, you will be not allowed to do that. Okay, but you can relax that by using swapping, where processes go in and out. Okay. Now the interesting thing about swapping is, while you are swapping, you can also run compaction. Okay, you roll out a process. When you roll it back in, you don't need to put it back where it was previously. You can give it any new space, any new hole, because you can simply use the new starting address as the relocation register address. Okay, it will just work just fine without any problems. Okay, so when you are using swapping, you can add compaction. Okay, so you can swap and defragment both at the same time. The only interesting thing that you need to keep in mind is, if a process is swapped out and it gets scheduled for execution, okay, it is not going to be able to run because it's not in memory. Okay? So swapping will interfere with CPU scheduling. In particular, CPU schedulers will not be able to schedule a process that is ready. It's in the ready queue if it is swapped out, because it's not present in memory. You will first have to bring it in. Okay, and remember that disk IOs are very slow. Okay, disk IOs takes tens of milliseconds. Instructions take nanoseconds or microseconds, depending on what speed processors you have. Okay. So if you have swapped out a process, until you bring it back in, which may take several hundred milliseconds, you will not be able to run. Okay, so you have to be careful that if you have swapping, you have to bring it back before it gets scheduled for execution. If you do not make that choice properly, you will have scenarios where there's processes getting scheduled, but they are not in RAM, so you will immediately have to put them back on the wait queue and try to bring in the process. Okay, so these problems do exist when you are swapping. Okay, any questions on this before we move on to paging? Okay, so the two limitations that we are going to try to relax is first, fragmentation is something we would like to avoid in a memory management scheme, okay, because it will result in, or not result, but it will require you to do compaction frequently. Okay. The second problem is in contiguous allocation, okay, there is limited room for the process to grow and shrink. Well, mainly to grow, it can shrink. Because if there's another process right next to it and you go and you malloc more memory on your heap, for instance, there is no way to allocate more RAM if there's another process right back. So you cannot smoothly shrink and grow processes. Okay? So if the process size doesn't change after it starts running, then there is no problem. But most processes will grow and shrink. As you create objects, deallocate objects, let's say in a Java process, or you malloc data structures in C or C++, the heap size will change on the fly. Okay, that will require more RAM or less RAM depending on what's happening. Okay? So process sizes do change over time. Okay, so that's another limitation we want to avoid. The third limitation is basically we want to somehow relax the restriction that the processes all have to be resident in memory at the same time. Okay, swapping does give you a way out, but we want to have better techniques that interfere less with CPU scheduling, for instance. So we look at paging as a way to address all of these limitations. Okay. So motivation for paging is very simple. Okay, it follows directly from what is referred to as the 90-10 rule. Okay. So 90-10 rule says 90% of the time a process spends time only touching 10% of its memory. Okay. So processes spend most of their time working on small parts of RAM. That doesn't mean that all of RAM is unused. So let's say this is a process A, okay, logical view of a process. At any given time, okay, it may be working on a small part of memory. Those may be the instructions that it's executing. Any data structures that is accessing in the stack or the heap is really all the stuff that is touching at any given time. Okay? Over time, the 10% of the region is touching is going to change as we start executing some other part of the process. Maybe it starts working on this part of the process or some other part of the process. Okay. So that region will change, but at any given time, a process only is accessing a small part of its memory. Okay. That's an empirical observation. So if you look at what a process is doing, what parts of its memory is it accessing during its execution, you will see that the 90-10 rule generally is followed by most process execution behaviors. Okay. So what does this observation help us do? Okay, how can we use this 90-10 rule to improve the efficiency of memory management? Yes. Okay, so you're saying let's break it up and do something interesting with each chunks. Okay, but I mean, what is the observation we have to make to lead to that conclusion that we can break up a process? Okay, what does the 90-10 rule tell you? Yeah. Okay, so in contiguous allocation, the entire process is in memory at all times when it's executing. Okay? The 90-10 rule says a process is only using 10% of its memory when it's executing. Okay? So then you should say, why should you allocate enough memory to hold the entire process when it's executing, when it's only touching 10% of its memory? Okay, the other 90% is not being worked on now, so why is that 90% in memory? Okay, you are essentially giving a process more memory than it needs to execute what it needs to execute now. So this should tell you that there is no reason to allocate enough memory to hold the entire process. Okay? It is sufficient to give it enough RAM to hold a fraction of its address space. And that's the fraction that it's working on right now. Okay, we'll come back to the notion of a working set. Working set is basically the set of memory pages that a process is accessing at any given time. So typically you do not need, for a process to execute successfully, you do not need to allocate enough memory to hold the whole process. It's sufficient to allocate only part of the process. Okay? So that's basically the next line here. It says keep only those parts of the process in memory that are actually being used. Okay? This will allow you to hold lot more processes than you could have before. Okay? Because you are now only allocating to each process maybe 10% of its total address space in RAM. The other 90% has to be kept somewhere. It's not like it's gone magically disappeared. You keep it on disk. Okay? So you allocate a portion on disk that's big enough to hold the process. Okay? Just as you did for contiguous allocation, but you keep the process on disk and you only fetch the parts that it's working on to memory at any given time. Okay? So essentially you are going to swap in parts of the process that you are working on and swap out parts that is not working. This will allow you to store or hold lot more processes in RAM than contiguous allocation. Okay? That's one observation we'll make. Now in today's lecture, we are not going to look at how do processes get swapped in and out, but we'll look at other parts of paging, which is what I'll come to in just a moment. Okay, so keep this 90-10 rule in mind. This is going to simplify, not simplify. This will make our life easier in terms of holding more processes and so on. It does complicate the memory management itself. Okay? That's the first observation you make. Okay? Second observation we will make is if you don't like contiguous allocation because it is limiting in some way, it doesn't let processes grow and shrink, you have to relax that assumption. Okay, so how will we relax the contiguous allocation assumption? Okay, there is only one answer. You do not allocate memory contiguously. Okay. So if you don't want to allocate memory contiguously, what does that mean? You will now break up a process into pieces. Okay. And different pieces of the process will get allocated to different regions of memory. You won't store the entire process in one chunk. You'll partition it into smaller chunks and you'll put them into different holes. That's how you're going to actually relax that assumption. Okay. In particular, what paging does is it requires you to partition the process into fixed size chunks. Okay. You could have made the chunks of arbitrary size. You could say, here's a process, I may sort of chop it up into 3 pieces of some different sizes and put them in 3 different holes. Okay. That's one way you can relax that assumption. But we will simplify that and say you always chop up a process into fixed size chunks called pages. Okay. And the page size is fixed, is determined by the hardware. Typically, it may be like, let's say 4 kilobytes. Okay? So you take any process. Okay? This doesn't matter how big it is. You will always chop it up into 4 KB chunks. If your page size is 4 kilobytes. Okay? And so you'll get some number of pages, and then you will just scatter. The pages will actually be scattered in RAM. They will not be stored contiguously. You allow now pages to be stored wherever you want. Okay? You find any frame that's empty, and you can store a page there. Okay? So this is going to get rid of external fragmentation completely. Because all you need to do is if you want to put a page in memory, you just find an empty page frame and you just put the page there. Okay, I'll show you a picture in just a moment. Okay, so paging is going to completely eliminate the problem of external fragmentation. There will no longer be an issue saying there isn't a hole big enough because you don't need to store the process contiguously. You can store it in any region of RAM where there is free space. Okay? So the logical memory of the process is still contiguous, but pages do not need to be stored contiguously in memory. Okay? So we have gotten rid of external fragmentation. We will not be able to get rid of internal fragmentation. Okay? The last page of the process may not be completely used. Processes can be of arbitrary size. Okay? You cannot force that a process size is a multiple of 4 kilobytes because you chose a 4 kilobyte paging size. So it may be the last page may have some unused space because the process size is not a multiple of 4 kilobytes. It's how big your code is. Okay? So you will approximately waste half a page per process. Okay? The last page you will waste some space. On an average, you will waste half of that page. Okay? So you will have internal fragmentation still, but it's only half page of a process. That's not a big deal. A process may have tens of thousands of pages. The very last page you will waste a little bit of space. Not an issue. The big issue that we have resolved is external fragmentation. Okay. Here's the picture now. Okay. This is a process with 6 pages, okay, that we have labeled A0 through A6. Okay. So those are the pages. They are fixed sizes. So you take this process, you chop it up into fixed size chunks. Okay. Here we have 6 of these chunks, 6 pages. This is main memory. Okay. And as you can see now, any page can be mapped onto any page frame. Okay. Main memory is also chopped up into the same fixed size chunks called page frames. Okay. So now you cannot put a page wherever you want. It has to be put into a page frame. It has to be slotted into some empty page frame. Okay. So you put page A0 in the second frame. Actually, is the third frame. It's F2 is the third. A1 has gone to F6, A2 has gone to F11, and so on. So if you see the layout, you'll see there's A0, A5, A4, A1, A3, A2. It's not contiguous at all. It's not even in order. Right? It's just arbitrarily scattered into page frames. Okay? This is what paging is going to do. You start using paging as your memory management scheme. Every process will be chopped up into frames. Frames will be allocated to memory. Okay, thus far, we are showing that all the pages are resident in RAM. Okay. For today's lecture, we are still going to make that assumption. Next time, I'll show you a generalized version of paging where only a subset of the pages are stored, the others are stored on disk. Okay. But for today, we'll still assume the entire process is resident, but it does not need to be contiguous. Okay. It's just scattered across RAM. Okay, so now you can ask, how do we actually implement paging? This is the basic idea. What does the OS need to do in order to implement this scheme? Yes.
Keep track of where each piece is in physical memory.
Okay. So the first thing you should realize is someone needs to maintain this mapping. Because the pages are scattered. For every process, the pages are all scattered. Okay, that someone is the OS. Okay, OS has to keep a table, okay, which we'll refer to as a page table, that precisely tells you this mapping. Say, where is page 3 stored? You do a table lookup and says that's where it's stored. Okay. So you need to now, because pages are not contiguous, okay, which is simplifying memory management, you need to keep extra information, which is precisely this mapping of where the pages are mapped into page frames for every process. And this data structure that you will maintain is going to be maintained in the process control block as well. Okay, we'll see how to implement that in a few slides. But that data structure is going to maintain this mapping for you. Okay, the first thing you need to do to implement paging. Okay, there's one more thing that we need to deal with. Thoughts on what that might be? Okay, so it has to do with addressing. Okay, now your assembly instructions are still going to have these logical offsets. Okay, that part has not changed. The compiler, when you compile source code, still doesn't know where the process is going to be stored in memory. Okay, in fact, it's not only not stored contiguously, it's scattered all across memory. This information that if you run this process, it's going to be laid out as shown in this picture is not known to the compiler. It can only generate logical addresses for every assembly instruction. Any assembly instruction that has a memory operand will have a logical address which is relative to the start of that process. Okay? So something still needs to convert logical addresses and that the CPU is executing into physical addresses. Okay? So there is going to be a need to do this address translation. The same thing that we showed you last time. Okay, if you remember this was the hardware that was used in contiguous allocation. You still needed to do the translation from logical to physical addresses. That part hasn't gone away. In fact, it has gotten a bit more complicated in paging because you do not have contiguously stored pages. Okay, so two things. One is you need to store additional information not just the start of a process, but a page table that figures out, or not figures out, but rather stores the mapping of pages to page frames. Second is you need to now design address translation logic that will convert, okay, any address, okay, any logical address into a physical address. And we'll see how to do both of those things. Okay. So we'll start with the address translation first. Okay. So the problem is the same that I just mentioned. How do we find addresses when pages are not allocated? Okay. So we'll still assume you generate a logical address, okay, which is a process is assuming that it is, let's say, processes of n bytes. So it still assumes, or the compiler assumes, that addresses go from 0 to n minus 1. Okay. So it's still going to generate an address saying I, which is the ith byte of the process. Okay. Now something has to translate this I into a page number and an offset within that page. Okay, that something is the paging hardware, and we'll see how to do that. Okay, so we'll have page tables, and we'll basically see how to do the translation. So this is the new hardware that you will use to generate physical addresses. Okay. The CPU will generate a logical address, okay, which is I. Okay. We'll take that and we'll split it into two parts, which is a page number and an offset within the page. We'll say which page does I reside in. Okay. We'll say it resides in let's say the jth page, okay, and there will be an offset within that page. So any address will translate into two parts, a page number and an offset. Now, once you've figured that out, that's still a virtual address. You have to ask, where is this page actually stored in RAM? Okay, because all you have done so far is said, when you have I, which page is it in and what's the offset? So you say it's in page A2 and it's the 5th offset. Then you have to ask the question, where is A2 stored? You look up the page table and you say that's the 11th frame. Okay, so you have to convert the page number to a frame number. That's what is being done there. You do a page table lookup. Okay, that's the page number. You look at that entry, the pth entry, and say, where is that page stored? It's in frame F. Okay, so then you basically say to go to this address, go to frame F, and look at byte D. Okay, that's really an address you have for memory. Okay. So you are going to take an address, break it up into two parts, a page number and an offset within the page. You are going to index the page table, okay, and find out where that page is stored that you are trying to access. That will point you to the page, to the frame number. And then you go and you access the offset within that frame, and then you're done. Okay, is that clear? So all of this has to happen efficiently, and we'll talk about efficiency in a few slides, but we're going to do some examples first. Any questions on this? Okay. So few things before we go to do an example. You have to realize that paging is a form of dynamic relocation. Okay? Just as in dynamic relocation, you have a start address and an offset within the page. For every page, now you have a start address, which is the frame, starting address of the frame. It's mapped to an offset within the page. So you can think of a page table as a set of relocation registers, okay? One for every page. In contiguous allocation, you had a single relocation register for the entire process, and you could use that to figure out the address. Here you have one entry for every page that's in the page table. Okay? Now the interesting thing is all of this translation is completely transparent to the process and even to the OS at some level. Okay, this is done in hardware. The compiler doesn't worry about it, even the OS doesn't worry about it. When the CPU executes an instruction, let's say you say add address I to register R1, okay? The hardware, okay, the CPU tries to execute the instruction, the hardware will take I, do that translation automatically on the fly for you and reference the right address. Okay? So it's completely transparent. The OS is not doing that mapping, the translation that I just showed you. That is being done in hardware. Okay? So in some sense, the OS and the compiler, none of them need to worry about the actual translation. The OS does need to keep the page table around. But once you have the page table, this translation is done in hardware. So it's invisible to the process. The process doesn't need to worry about it. Okay. We still have protection, okay, which is going to tell us how things are going to work with respect to not accessing something that doesn't belong to you. So if there are, let's say, 10 pages for this process. If you try to access the 11th page, you're going to get an error saying you're trying to access memory that's not allocated to you. Okay? Same thing we did with limit registers, you can do here, okay, which is not shown, but that's what you can do. Okay? So protection is provided with the same mechanisms as dynamic relocation. Okay, so now let's think about how we are going to build this hardware in a little more detail. Okay, and then we will do an example. Okay, that will just translate this, whatever is in this slide, directly to an example. Okay, so I just asserted that given address I, okay, that you, let's say this is a process. It is laid out and it has n bytes, 0 through n minus 1, and it's trying to access address I, and I is the ith byte relative to the start of the process. I simply said, oh, you can take I and you part it and you break it up into two parts, a page number and an offset. And nobody said, how is this done? Okay, how is this magic? How are you magically extracting the page number and an offset? Okay, so let's explain how that is done in just a moment using this simple example. Redraw this. Okay, first we'll do it using some simple example. So let's assume you have 4 byte pages. A very trivial example. Okay, so this is page number 0. Okay, that's 4 bytes. Okay, this page 1, page 2, 4 bytes. Okay, so this is a 12 byte process. It has 3 pages, 0, 1, and 2. Okay, so if I give you address 5 and I ask you which page is it stored in, okay, what would you say?
Page 1.
Okay, it's in page 1. The first 4 bytes are here, the 5th byte is here. So actually, that's the 6th byte because you count from 0, but it's still in page 1. Okay, so simply what you have done is you take an address I and you divide it by the page size. Okay, that's the page number. Okay, so you took 5 and you divided it by 4, you get 1. Okay, integer division. Okay, so if I said that's what you essentially did, right? You basically divide it. So if I had said page number 10, you would say that's here. Okay, because that's the first 4 bytes, that's the next 4 bytes, and then the 10th address is actually going to be there. Okay, so 10 by 4 will give you 2. Okay, the offset within a page, okay, is simply I mod the page size. Okay, so if you go back to our address 5, let's say what's the offset? So you said it's in page 1, then I say which byte of page 1? That's the offset. Okay, you would have basically have to say that's the second. Okay, this is address 0, that's address 1 within the page. So this is address 5. Okay, so this is address 0, 1, 2, 3. That's the first 4 bytes, 4 and 5. So offset 1. Okay, you simply do 5 mod 4. Because the page size is 4, that gives you 1. Okay, 5 divided by 4 gives you the page number, 5 mod 4 gives you the offset within the page. Okay. So given any page size, if you are given an address I, the way you find which page number and which offset within the page is you simply divide that address by the page size, you get the page number, you do mod of the page size, you get the offset within the page. Okay, that's what that hardware will also do. Is that clear? Simple arithmetic. Okay. So now, given that, we'll see how do you extract. So simply what the hardware has to do is given any page number, not page number, any page size, given address I, it has to do a division and a mod to figure out the page number and the offset within the page. Okay, so this P and D that I was showing you here. Okay, so if you give given I, this is what you'll get by just dividing by the page size, and this is what you get by doing the mod. Now the nice thing is if the page size is some exponent of 2, it's some 2 to the power m, then this division and mod you don't actually have to do. You can simply look at the bits of an address and extract that automatically. So it's the same as doing this arithmetic. So in the special case where page sizes are some exponent of 2, okay? Page sizes 512 bytes, 124 bytes, 2048, 4196, which is 4 kilobytes, is 4196. If it is 2 to the power something, then if you basically plug in the page sizes 2 to the power, what does it say again? So this is what you're doing, because the page size is now 2 to the power m. Okay? Then all you need to do, this is the same as looking at the high order bits and the low order bits of any address I. Okay? Because the division is the same as looking at the high order and the low order bits. Okay? Is that clear or not clear? I can show an example to convince you a little more. Okay, what the page size in our example was 4. Okay, that is an exponent of 2. Okay, that's 2 to the power 2. Okay, you write out all the addresses. Let's say address 0, 0, 0, 0, 0, 0, 0, 0, 1. Okay, and so on. Okay, this is address 0, this is binary. Okay. This is binary for 1, binary for 2, 3, 4, 5. So we are just writing numbers, integers in binary. Okay. Now if we want to do 2 to the power, okay, so we said we want to translate address 5, correct? 5 by 4 was 1. Okay. If you simply take the high order bits, which are those 2 bits, what do you get? What 0, 1 in binary? I hope people know binary arithmetic. Okay, so 0, 0 is 0, 0, 1 is 1. Okay. So that's same as 5 by 4. Okay. And the offset was again 5 mod 2, that was 1. So if you take the low order bits, you get the offset. Okay. What we are simply saying is, in the special case when the page size is some exponent of 2, you don't really need to do the division and the mod. Looking at the high order and the low order bits actually allows you to do the division without doing a division and a mod. Okay. Because that's what you will get when you divide by 2 to the power something. You are simply doing left shift and taking the high order bits. Okay. That is essentially what is shown here, where it says that the page size is some exponent of 2. Given any integer, take its binary representation, simply look at the high order bits. Okay. That is equivalent to the size of the process. That will give you the page number. Look at the low order bits, depending on the size of the process, that's going to give you an offset, and you're done. Okay. Doing that is essentially the same as equivalent to doing this. You could have actually implemented a division logic, it would have given you the same answer. But looking at bits, as you can imagine, in hardware is much faster than doing a division. You're simply looking at some bits there. Right? So this translation can be done very efficiently. In the special case, when you set page sizes to be some exponent of 2. This is why on most hardware you will not see some arbitrarily chosen page size. You will always see something that's some exponent. 4 kilobytes is 4196. Okay, that's a typical page size that you find on most hardware. There is a reason for that, because it makes this translation into page number and offset trivial. Okay, you don't actually have to implement some hardware to do this division or mod. If you had picked an arbitrary size page, you would have to do that. You would actually have to implement hardware that is going to do this division on the fly for you, or mod. Okay, is that clear? Yes? Okay. So now if it's clear, let's do an example to do exactly that. Okay. So this is the picture that's given to you. This is RAM. That's a process. Okay. Process has 4 pages that go from A0 to A3. Okay. RAM is 256 bytes. Okay. Page size 16 bytes. 2 to the power 4. Okay. Memory size 256, 2 to the power 8. Okay. 4 pages for a process. That's the page table. Okay. That's simply telling you where the pages are marked. This is the same example that I showed you. It says page 0, okay, which is that page is stored in frame 2, which is here. That's page 1, page 3, page 2. Okay, that's how it's laid out. So you see this mapping 2 to 11 is here, 3 to 9 is here, and so on. Okay. So this page is essentially stored there, that page is stored here, and so on. Okay. That's how your process is laid out. Okay, so now you are going to do some translation of virtual to physical addresses using this picture. Okay, any questions about the picture? Okay, so first question is, how big is the page table? Okay, that should be trivially answered by saying 4. Okay, that's already shown to you. Okay, so 4 pages. Second question is asking is, how many bits do you need for an address? Okay, so if you have a memory of size 256, how many bits do you need to address that memory? Yes.
8.
You need 8 bits because addresses go from 0 to 255. Okay, so you need 8 bits to go from 0 to 255. Is that clear? This is a 8-bit hardware. You hear the term 64-bit hardware and 32-bit hardware. That should tell you what that means. That basically says addresses can go from, if it's a 64-bit hardware, can go from 0 to 2 to the power 64. That's how large a process can be. That's how large RAM can be. Okay, because that's how large the address can be. If you have 8 bits, you can only address RAM that goes from 0 to 255. Because you cannot have addresses bigger than that. Okay, so RAM 8 bits. Okay, so 8 bits for an address. And now it says which part is the page number and which part is the offset within the page. So you are given 8 bits. Okay. Some of those high order bits will be the page number. Some of the low order bits will be the offset within the page. Okay. Question is, how many bits do you need for the page number and how many bits do you need for the offset within the page? Somebody said 4. Okay, that's good. Why is it 4?
Well, it's 8 in the first half because the page size and the second half is the offset.
Okay. So you have 8-bit address. Okay. What's the page size? 16 bytes. So each page here is of 16 bytes inside. So the offset inside a page can go from 0 to 15. Okay, how many bits do you need to address 0 through 15? 4 bits. This doesn't need a calculator, right? So page offsets go from 0 to 15. So you need basically 4 bits. Okay? How many pages do you have? How many frames do you have? You can see that they go from 0 to 16 also. So page numbers will go from 0 to 15 as well, because you can say you have essentially frame 0 through frame 15. So page numbers will also go from 0 to 15. That also needs 4 bits. Okay? So you take your 8-bit address, okay? You partition it into 2. The low order 4 bits will give you the offset. The high order 4 bits will give you the page number. And that you index the page number into and get a frame number. Yes.
So do we need a page table of size 16 then?
Okay,
Rather
good
than
question.
just 4?
So the question is, do you need a page table of size 16? If you can, the maximum size page table will be of 16 in the case where the entire memory of the process is resident in RAM. Okay. So a process in this case cannot exceed 16 pages. Okay, that's the maximum size. This is a smaller process, so it only has 4 pages. But if I ask what's the maximum size process that you can accommodate, you should say if there are 16 pages, it's 16 pages long. So that's a page table of size 16. Yes, you're right. Okay, is that clear? Okay, so now if that is clear, then given address 24 for this process, we need to do a translation. Okay, you can do this one of two ways. You can do this the old way by just simply plugging in, simply doing this. Okay, now address is 24, so you're simply going to do this. Okay, or you write out 24 in binary representation. Okay, and you pick its low order 4 bits and high order 4 bits. That will also give you the page number and an offset. They will give you the same answer. It doesn't matter how you do it because you are not hardware. We are asking you this as a question, so you can decide whether you like to do it this way or this way. Okay, the hardware will always do it this way. Okay, so simply to translate it, if you say 24 by 16, that should say that's page 1. Okay, this is an offset, so it's 8. Okay, so when you ask where is page 1 stored, which frame is it stored in? You have to index the page table to find that. Okay, so you'll say where is page 1 stored? You index 1, stored in frame 6. It's right there. Okay, so 1, 8, this will get translated to 6, and then this is offset. So this is the frame number, and that's the offset within the frame. Okay, so given an address, you first find out what page number and what offset. You take the page number, you index the page table, and then you find the frame number and an offset. That's going to give you the real address. Okay, so we are looking at the 8th byte of the 6th frame. Okay, so 6th frame starts at 96, so that's really address 104 that we are looking for. Is that clear? Okay, so here it is. That's essentially what that is. Okay, so a slightly different question here, which is saying, that previous example, assume that you can address each individual byte of memory. Okay, typically, you will not be able to do that. You can address memory in words rather than bytes. Okay, if you have a 16-bit architecture, okay, you will basically be able to address 16 bits as one word. You cannot address those individual 2 bytes of that 16 bits individual. Okay, so addresses will address words, not bytes. Okay, so here we are saying you have 4 byte increments. This is a 32-bit machine because 4 bytes is 32 bits. In 32-bit machines or 32-bit architectures, if you rather than thinking of memory as byte 0, byte 1, byte 2, byte 3, these first 4 bytes will actually become one word. So you think of them as laid out like this. So these 32 bits become one word. The next word is going to basically be 4th, 5th, 6th, and 7th byte. It's accessed as one word. That's how 32-bit machines work. Okay, so what I showed you previously was a very simplified 8-bit architecture where you could actually address individual words. In reality, depending on what hardware you have, if you're 64 bits, you will be able to address 64-bit words and not individual bytes within the word. You have to address the whole thing and access the whole thing in one go. Okay. So now the question is slightly different. It says assume that you can address RAM in one word increment, and each word is 4 bytes. So then it's asking what part is P and what part is D. It's asking you to translate address 30. Okay, so I'll show you the example again. Okay, so this is basically now you can think of each of these as 1 byte. Yeah, so you're addressing 4 bytes at a time. Okay. Page size 16 bytes. Okay. You are addressing them in 4 byte chunks. Okay. So how many addresses do you have in a page now, rather than 16? So you will have 4 addresses because you will have the first 4 bytes addressed as one word, the next 4 bytes as the second word, third word, and 4 words. So you have 4 words in pages, so you need addresses that go from 0 to 4 within each page. Okay? That requires only 2 bits, not 4 bits as previous. Okay? Because addresses are now only going from 0 to 4. You cannot no longer address individual bytes of a word, you address the whole byte. Okay, so now you need fewer bits because there are fewer addresses to look up. So the offset is now only going to require you 2 bits, not 4. Okay, nothing has changed as far as the page size and number of pages is concerned. It's still 15 pages, so you still need 4 bits to go from 0 to 16. Okay? But your address itself has shrunk from 8 bits to 6 bits simply because we said that you can no longer address individual bytes. This is a 32-bit machine, so you have to address entire words. So to do that, you need fewer bits. Yeah. So you need 6 bits, 4 for the page, 2 for the offset, and then that's the translation, which I'm not going to go into. It's the same kind of example. So now this is the, remember, this is the 13th word, not the 13th byte. Okay? 13th word, because these are 4-byte words, is actually byte number 52. 13 times 4. Okay, so we are actually, when we say virtual address 13, that we are asking you to access the 52nd byte of the process, because that's the 13th word of the process. Okay, that's how you need to do the translation. Okay, you'll still do this. Okay, so you just do 13 by 16. You actually, the easier way to do this is probably just plug in this and do it. Okay, and divide by 8 and so on. Okay. So I will not go into that. Instead, let me talk a little bit about context switches and making paging efficient. Okay. So until now, I showed you this table, that's the page table. Okay, we never said how is it implemented in hardware. Okay, this is something I said hardware implements for you, but we didn't say how to do it. Okay. So there are few different scenarios. The first one you can say is keep the page table in registers. Okay. If you keep the page table in registers, page table lookups are going to be very fast because the register is the fastest piece of memory you have in the memory hierarchy. Okay. Now, limitation of keeping the page table in registers is that you cannot have large page tables. You have a limited number of registers. You have 64, 128 registers. Okay. You cannot say I limit the size of a process to 64 pages. Okay, then your process may not even be 1 megabyte in size, let alone hundreds of megabytes. Okay. So if you put the page table in registers, you get very fast access to the page table. Disadvantage is you are limited by the number of registers you have. On most hardware, that's going to be few tens at most. So your page sizes, or rather page table sizes, will also be limited. Okay? That means you cannot have very large processes in your system. Okay? That's a fundamentally bad limitation. Okay? So you cannot store the information in registers. Where else would you store it? You would store it in RAM. So RAM can say rather than storing the page table in registers, you store it in kernel address space. Okay? The kernel, where the OS is keeping maintaining the page table, so it can keep that page table in memory, in its own memory. Okay, so the kernel will have a page table for every process. It's going to stick it into the process control block. Okay, that's the data structure that's maintained in kernel memory. Okay, so if you do that, what would be the advantages and disadvantages of that page table implementation? So we have no longer any restrictions on the size of page tables. Page table can be as large as you want it to be because your OS can take any fraction of RAM and so can any data structure that the OS maintains. So we have effectively eliminated any limitations on the sizes of page tables. And sizes of page tables map directly into sizes of processes. Processes can be as big as you want. Okay, subject to the size of RAM at this point. Okay. So that's an advantage. Disadvantages? Yes.
You have to add another memory lookup for every memory lookup.
Okay. So disadvantages, this is going to have very bad performance. Efficiency will suffer quite a bit. Okay. And the reason for that is because your page table translation, okay, when you are given a virtual address, you are going to look up a page table. Okay. The page table is in RAM, looking up the page table is a memory access. Okay. So any instruction that requires a memory, has a memory operand, will involve another second memory lookup just to do the address translation. Factor of 2 slowdown for every instruction that accesses RAM. Because you have to first access RAM to figure out what the address is, then you run the instruction which also accesses RAM. Yes.
Would you also have a context switch too?
Would you have a context switch in that situation? Typically, you won't need a context switch because you're simply going to have the hardware look up where the page table is in RAM and get it from there. We will talk about another scenario where there might be a context switch, but not in this case. Okay? Because you can directly address memory without having to do any context switches. The hardware can also access memory. Okay? So very bad performance, but no limit on the size of processes. Okay, so now you are given these two choices: good efficiency but small processes, or pick large processes but bad performance. What would you do? Where you make trade-offs. So you say, as a OS designer, should I tell my users you can have little processes but they'll run really, really fast? You can have big processes but your performance is going to be very bad. What would the answer be? Pick. Yes.
Small processes that are more efficient.
Can you speak up? I'm not hearing what you say.
Small processes that are more efficient.
Small processes that are
Efficient.
efficient. That's what you would like. Okay. Everyone wants bigger processes but poor performance. Okay. Nobody wants to say anything. So you should say neither. Okay. Neither of those two are good options. We like the efficiency of the registers, but we also like the flexibility of keeping the page table in RAM. Okay. If you say I want both, you should be greedy. I want both of those things, but neither of those limitations. Okay, so question is, how do you get that? Okay, yes.
Are we assuming no cache? I mean, you could keep it in a like level 1 cache or something like that.
Okay, so we will use a level 1 cache because I was leading to that. So the point is, both of those schemes actually have something going for them. Okay? So registers are fast, memory is not limited. Okay? So you can keep larger processes, and registers allow fast lookup. So let's say, but we don't like the disadvantages of either of those two. So if there was a middle ground, you want to basically get those two advantages. So what can we do? Okay, exactly what was just proposed here, saying keep the page table in memory. Okay, so now you are no longer limited by the size of the process, but performance is poor. How do you improve performance? Okay, use a cache. Cache is basically faster memory. But you cannot keep the entire page table in cache. That's going to be expensive. Then you could have as well stored the page table in cache. Why keep it in memory to begin with? You only want to keep parts of the page table in cache, not the whole page table. Okay? And this is where the 90-10 rule is going to help us. Okay? Because in the 90-10 rule, I said the process is only accessing 10% of its memory at most at any given time. What does that tell you? You will not need more than 10% of your page table entries to be kept in this cache. It's not even 10% because that's 10% of memory. Pages are sort of entire chunks of memory. So you may need only a few page table entries to be cached. Okay? So we'll use a special kind of cache called the TLB, Translation Look Aside Buffer. When I introduced this in lecture 2 and said, do you remember this from 230? People said no. So I'm going to reintroduce what this is. Okay. So it's essentially a fast cache. Okay. Here's a picture of what this cache looks like. This is your page table. It is actually stored in memory. Okay. What you will do is you will take the page table entries that the process is currently working on. Okay, so let's say that's a page that the process is currently accessing. The first time you access that page is not going to be in the cache. You'll have a cache miss or a TLB miss. Okay? But then you go to memory and you fetch that entry from the main memory page table. You stick it into the cache. Okay? Next instruction, probably in the same page. Next time you access that page table entry or try to do this translation, you already brought this entry into the cache. Cache is much faster. Lookup is going to go much more faster for you. Efficiency will go up. Okay, so we will keep a subset of the page table in faster caches, in particular in the TLB. Okay? TLB is going to be shared across all the processes in your system. Okay? So each page table, each process has its own page table. Each page table will have a few entries that are actually stored in the TLB, and this will have entries from a variety of different processes. Okay? So this is like a hash table. It's an associative memory. It's a key value lookup pair. You say for this process, what do I look up? So that's what you see. So whenever you generate a virtual address, you find a page number. You first look up the TLB, saying is the page table entry already in the TLB? If so, you find the frame number, you're done. Okay? If it's not in the TLB, you have what's called a TLB miss. In the first case is a TLB hit. You have a TLB miss, like a cache miss. You'll go to the page table, fetch that entry, stick it into the TLB. So all subsequent accesses are sped up. But this instruction is out of luck. It's going to be slowed down, okay, by a factor of 2, but that's okay. So then you will fetch the page table entry, execute this instruction, but subsequent instructions that access the same page will be sped up. Okay. Now this is a limited size cache, so it cannot just keep getting entries from the page table. When you bring something in, you have to throw something out. Okay. You have to do TLB eviction like you do in any caches. Okay, so entries that haven't been accessed for a while can be overwritten, for example. Okay, so TLB management will not look at here. The fact that you have a TLB. So this is what the hardware will give you to speed things up. So the page table is in main memory. You don't need anything special for that. But if the hardware supports a TLB, you will have significant speed up in your page table accesses. Okay? So this is the new translation logic. Okay, we added one more entity here. So you take your virtual address, you're going to do this, okay, or essentially that. Look at the low order bits, high order bits, give your page number. First look at the TLB. If the entry is there, you're done. If you have a TLB miss, go to the page table, fetch the entry and then execute the instruction. Okay. Then subsequently, hopefully, you will not have another TLB miss for a while. Okay. So this is how we are going to achieve the efficiency. TLB is a cache that is almost as fast as registers. Registers are faster, but level 1 caches are not bad. They're still pretty fast. Okay, much faster than main memory. So you have gotten an efficiency boost. And we are still not limiting the page table sizes or anything. Page tables are stored in main memory. They can be as large as they want. We'll only fetch the entries from the page table the process is working on because of the 90-10 rule and stick them in the TLB. And so you'll get efficiency. Yes?
How often do you check to see that the values in cache are still valid?
Okay, so how often do you check whether the values in cache are still valid? You'll see that there's a valid bit here that simply says whether the entry is valid or not. You are not actually going to do any special checks at all. Okay? What you will do is the process will simply continue execution. Every address you will do this translation, and if basically the entry is there, you do nothing. You simply go and execute the instruction by doing the translation. The entry is not there, you'll fetch something. So whenever there's a miss, you'll fetch something and you'll evict something. So there is no extra check done. It's only during the execution that all this is going to happen. Okay, so no special management. You simply fetch the entries that are being accessed and you put them in the TLB. Okay, is that clear? Okay, so now let's ask the question. So what have we actually gotten in terms of memory performance? Okay, question there.
Why is there a valid bit? Why don't you just remove it when the reference isn't valid?
Okay, so why is there a valid bit and why don't you remove it when the reference is removed?
Yeah, like if the valid bit says false, why not just remove it from the TLB instead of having it stay in the TLB and say it's not valid?
So the valid bit is simply whether the TLB entry is empty or not. Okay, there may be some garbage there, right? So some other process may have left something there. Okay, so when you start execution, you can invalidate things and so on. Otherwise, you don't know whether there is some integer here and some integer there. You don't know what that is. If you do some garbage translation, you will get some error. Okay, so that is just to tell you whether whatever is stored there is not zeroed out or anything. Whatever has been stored there is still there. You simply overwrite. Okay. So now let's analyze performance. Okay, so how much speed up did we really get as a result of TLB? Okay. So first we'll ask if the TLB was stored in memory, what is the effective cost of a memory access? Yeah, we already said the entire page table is in memory. There is no TLB. Okay. For every instruction that has a memory operand, you have to do a second memory lookup just to access the page table. Okay. So the effective cost of memory is 2 lookups for every real lookup that you perform. Okay, so if you say M is the cost of memory lookup, cost of a memory lookup or the time to do a memory lookup is M. Okay, so if you have the TLB in memory, let's say MA memory access, and effective memory access is 2 MA, twice the cost. That's what we said. Every time you have an instruction with memory operand, second memory lookup. So 2 memory lookups for every instruction that has a memory access. Okay. Now we say, if you stick in a TLB, how much speed up did we get? Okay, yes.
It's strictly greater than 1 MA, but less than or equal to 2 MA.
Okay, so if you had registers, and we'll say registers are so fast that we'll neglect cost of accessing a register, then you are basically at MA. Every time you access memory, you are simply going to go look up a register and assume that that cost is effectively 0 and do a lookup. So if you are completely in memory, you are 2 MA. Okay, if you have a TLB, you are going to be somewhere in between. That's what you said, right? And our question is, can we come up with an expression to show what that is? Right? So for this, we have to assume that whenever you do a memory lookup and there is a TLB, there is some probability P, okay, with which the entry is not there. That's the probability of a TLB miss. Okay. So probability of every time there is a miss, what is the cost of memory access? Okay. Every time there is a miss, you have to go to main memory and look up the page table. Okay, so that's twice the cost. Every time there is a hit, so we'll actually make that more precise. It's a 2 MA plus TLB. You first look in the TLB, that's a miss. That's the cost of a TLB lookup, and then you are 2 MA. Okay? And so every time there's a hit, what's the cost? So you first look up the TLB, the entry is already there. You are going to then simply go and access memory. Okay, is that clear? Now we are going to basically say this is the probability with which there is a miss. So every time there is a miss, this is what's going to happen. What's the probability that it's a hit? Okay, 1 minus P. Yes. Elementary probability. It's either the event happens or doesn't happen. That's the probability of it happening. The probability of it not happening is 1 minus P. Okay. So this is your expression that we are going to say is the cost of an. Okay. Now, depending on the hit rate, so if the this event happens very rarely, this probability is going to be close to 0. Okay, most of the time, if you have hits, the probability of a miss is very, very small. It's close to 0. So this side of the expression is going to become diminishingly small. Okay, so it's going to be very small because I'm multiplying it by a quantity that's very small. So effectively, the memory access is going to tend towards this, because this expression is going to tend to 1 in the limit. So your effective memory access is going to be looking like that, okay, when you have high hit rate. which is basically you just do a TLB lookup, which is very fast, and then you effectively do it. So you are going to trend towards MA as the probability of a miss trends towards 0. Because as it trends towards 0, this expression will start becoming very small, this expression will start dominating, and that's what you will get. Of course, if you have very poor performance, if you have very badly behaved processes that do not exhibit the 90-10 rule, they just start randomly accessing arbitrary pieces of memory, get lots of TLB misses. Most processes don't misbehave, okay, they are well behaved. But if you have misbehaving processes, this entry will start getting larger, you will start effectively becoming, seeing that performance. Because every TLB lookup is going to look like a miss. Yeah, it will be a TLB miss, so you will pay the price of 2 memory accesses. You fetch that entry, next instruction looks up some other page, again you have a TLB miss, and so on. Okay? So for well-behaved processes, you will not see this. You will basically start trending towards TLB plus ME. Okay? So that's basically what is shown there, except that here, this probability P is the probability of a hit. In this expression, I said P is the probability of a miss. It doesn't matter. One is P, the other one will be 1 minus P. Okay? Any questions on this? So this allows you to analyze by sticking in a TLB, okay, what kind of speed up do you get? And the answer is it depends on the TLB hit rate and the miss rates. But for most well-behaved processes, the cost of putting a TLB will be well worth the boost in performance. Okay, so there's a designer, you will say that's what you are going to say. That you don't like either of those two, so you try to get the best of both worlds. Okay, that's how you will do this. Okay, so some very quick things and then we will end. So here, now that we have paging, okay, there are extra work that has to be done in order to allocate page tables, deallocate page tables, and so on. Okay. So this is all that you have to do when a new process comes into memory. Okay, we are simply recapping. Process comes in, says you need K pages. Okay. So basically you say, are there K frames free in memory? No longer there is a need to have them contiguous. So you are going to just say, if K page frames are free, then you simply take K arbitrary free frames and allocate them to a process. You construct a page table saying the first page is put here, second page is put here, and so on. Okay, so you'll basically construct a page table. Okay. You'll mark all TLB entries as invalid, okay, because anything that's there is garbage. You haven't actually fetched anything from the page table. You start the process. As the process executes, every time you have a TLB miss, you'll start fetching page table entries and sticking them into the TLB entry, and then you'll make the bit valid. Okay. And then that will allow you to have TLB hits. Okay, so that's all initialization. Quick stuff about context switches. So every time you switch between processes, you have to now do extra work. The page table, okay, if it's in memory, you don't need to do anything. Okay, so what you will do is you will take the page table base register. Okay, you still have to keep some track of where the page table is stored. There's a register for that. That you will copy into the PCB, process control block. If you want to start with a warm TLB, okay, you'll also copy the TLB into the process control block. That's purely optional. You can simply discard whatever is in the TLB. So next time that you start executing, you'll start with a cold or an empty TLB. So first few instructions you'll see misses. Okay. So you could do that, or you could save the TLB and on the context switch you can restore it. So you start from where you left off. Okay. You can use either of those two approaches. So this is an optional step. So you copy store the state of the TLB, you flush it, and mark all the bits invalid. You restore the TLB if it was saved, restore the page table register, and then you're ready to go. So in addition to saving and restoring registers, you have to also save page table base registers and optionally the TLB. Extra work to be done on context switches because you put in more hardware to deal with memory management. Yeah, multi-level paging we are going to skip. Just one last point. It's an important point is now that you have pages, you can actually share memory across processes. Until now, we have said a memory that has been assigned to a process is its own memory. No other process can access it. We can now relax the restriction and allow pages to be shared. The way you share pages is, let's say that's a shared page. There are two processes which has page table 1 and page table 2. The way you will simply share it is make both page table entries actually point to the same page frame. Okay. This is a region of RAM. If you have page tables where page table entries from two different processes are pointing to the same region of RAM, you will essentially have this page appear in two processes. Okay, now you can share memory across processes. This could be used for shared libraries. Typically in most OSs, you will only have one copy of the library loaded in RAM, and that library is shared across all processes. Like the JVM or the C library, you will not load that code multiple times. You may just load it as a library and keep it there once. Any process that needs to use it, you will not load it from disk again. You will simply make the page tables point. Okay. Or you can have actual shared memory. If you want to do producers and consumers across processes and so on, if you explicitly allocate shared memory, this is what's happening. The OS is allocating a special region and making it available to two page tables. So this is only done in special cases. You don't want to arbitrarily start sharing memory and have processes trample on one another. But where your libraries or your shared memory regions, you can do that here, which you couldn't do in contiguous allocation. But now you can have processes that can actually share RAM, right, using pages. So this is something to keep in mind. Okay, so that's all that we have. We are out of time as well. So we have basically come up with a better scheme, and we will continue next time with a further enhancements to paging. Okay, so this is it for today.